presentation about how Edmodo, an educational technology company, handled the huge traffic growth during the first weeks of the pandemic last year. We hit several bottlenecks and we faced several difficulties. And in the next 30 minutes, we are going to try to show you how we overcome these problems and how we kept the site up and running. My name is Miklos Szel. I'm Senior MySQL Architect at Edmodo. And let me introduce my colleague, Nat, whose help was invaluable during these difficult days.
Thank you, Muka. I'm going to start by giving a brief intro about our company, Edmodo. Edmodo is an educational website that takes the idea of a social network and refines them and makes it appropriate for a classroom. Using Edmodo, students and teachers can reach out to one another and connect by sharing ideas, problems, and helpful tips. A teacher can assign and grade work on Edmodo. Students can get help from the entire class on Edmodo. Also, parents can join the class to bring a level of transparency to this setup. It was founded in 2008 and now has more than 140 million registered users. Edmodo is hosted on AWS. The DBs are in AWS EC2 instances. We have a single writer, multiple reader architecture. These are Percona servers with asynchronous replication. We have divided our DBs into 13 different clusters based on read, write, load, and for reasons like avoiding single point of failure. Before March 2020, we had 13 writers and 34 replicas in our DB fleet, and we were using the instance types that you can see in the presentation, and we use GP2 disks for the DBs. The peak DB load we handled before March 2020 was 200,000 queries per second, and it usually comes around August to September when we hit the back to school period. All the application web servers, they run inside a Docker container or under AWS autoscaling groups. This helps us with automatic scaling and other health check replacements. And we use memcache and Redis for caching. Things started changing quickly starting March 2020, both inside and outside the company. The world was getting really hit hard by the COVID pandemic, and all of us were facing a lot of challenges. Our usual increase in traffic comes around August, September during the back to school period. Starting March, we started to see a slow increase in traffic for our website. The code that you're seeing right now is from our boss, Chris, to the company in the second week of March. He had said at a guess, this could probably be due to COVID. The increase in traffic slowly started making sense to us as schools that were closed due to the pandemic were trying to find remote learning solutions. With the increase in traffic every day, the number of app servers started scaling up and the latency of the website was slowly increasing. Every day was a surprise and challenge from the second week of March, and there wasn't really a good way for us to predict the traffic to the website at that point. And we really didn't know how long this was going to last, and we started hitting some limits. In 3 to 4 weeks time, as you can see the metrics here, our daily active users grew almost 4 times. The number of requests our app was getting every day increased by almost 10 times. The peak requests per minute our web servers were handling increased almost 14 times. Normally, the peak traffic for us comes in morning US time, but we were achieving peaks in totally different times in a day than we're used to, as our European traffic started growing, mainly Italy, as the pandemic had halted the entire nation. We hit a DB peak of 5 million queries per second, and this was almost 25 times more than our previous peak. So we had to increase our site capacity by at least 15 times in this period. A small intro about our existing monitoring and configuration management setup. For monitoring our DBs, we use the following tools. Due to the sensitive nature of our data, we mostly employ on-premise monitoring. We use the open source tool Percona Monitoring and Management. We have custom dashboards built for us to show the system level monitoring overview of MySQL, cluster level overview, details about replication, etc. that are key in debugging ops team issues. We also use Nagios to monitor the health of our DBs. We have custom alerts from uptime, disk limit exceed warnings, replication lag, to even alerts like max value check for our integer columns in our DB. Vivid Cortex, we only have 2 licenses for this, and hence it is only on our most important clusters. But this is a cool tool that gives us in-depth details about the queries running. This helps us identifying problematic queries so we can work with devs on optimizing them. PT stock, another monitoring tool that collects useful information, and when things go south, say the number of threads connected is really high, we can have the output of the show process list, InnoDB status, PS aux, etc. And then AWS CloudWatch is also useful in monitoring the health of the DBs. We have Ansible as our config management tool, and this makes our life simpler by automating things for our DB deployment. We have a Dockerized MySQL admin Linux box, which we use to deploy new machine. Maintaining the inventory file is a slightly hectic task when working with AWS, as it has frequently changed IPs, auto-scaling instances, and much more. With Ansible Dynamic Inventory, we can get this info from AWS in runtime. The automation takes care of creating the EC2 instance along with the EBS volumes for it, takes care of assigning security groups, and has features for OS tuning as well. It installs MySQL with our defined configuration and takes care of the replication as well. We have regular backups for each DB cluster that are uploaded to S3. And for the source of a new DB, we have options for either restoring it from an S3 object or using a donor machine as source, and the data is copied using an extra backup stream. Once the replication is caught up, the automation also takes care of installing our monitoring tools on the new machine, namely PMN, Nagios, and PT stock. It updates the corresponding CNAMEs on Route 53 or cloud domain name system and sends us a Slack notification once the machines are ready. The traffic was hitting new records every single day in March, and the weekends were the only time in which we could start planning for the next week. And we would see a record every following Monday. And because of this, the queries that would normally perform well for smaller tables started struggling owing to the sudden growth of some tables. And there were some limits that we simply didn't expect. With the increase in traffic every day, we're going to share with you what we did to handle this during this period. The first natural step was to scale for reads. We started to add more readers to our big clusters on a daily basis. We started upgrading the instance types for all the machines to more powerful ones so we could handle the load better. This was possible with our existing Ansible automation, but we had to manually warm up the machine once the machine was ready and put it to serve broad traffic. This helped for some days until we hit another bottleneck with the MySQL connections. Our backend is written in Ruby on Rails, and we have a limit wait timeout equal to 600 seconds, but Ruby MySQL to connector executes the command you see on the slide when it establishes a connection and overrides the default wait timeout. So there were idle threads for more than 600 seconds, and it started maxing out connections in our big clusters as our app server started increasing linearly with traffic. We increased the max connections on all DB clusters as a first step, and even that didn't help after a while. We ended up killing the idle connections that were connected for more than 600 seconds, and that eased the load up a bit. But around 2 million queries per second, the previous solution wasn't a sustainable one, as some of the source servers started crashing. We had to change our architecture a bit to support this increase in traffic, and we're contemplating about using ProxySQL at that time to help with this. Mocha will now talk about the role of ProxySQL, a few architecture restructuring that we did, and other improvements we managed to do in this period to survive the onslaught. Over to you, Mocha.
So the rollout of ProxySQL was not immediate. We created some new servers with the automation and installed ProxySQL on top of it. And we evaluated ProxySQL a couple of years ago, but decided that it would actually introduce a bad habit of devs not fixing their queries, but instead they would rely on the ops to start rewriting it with ProxySQL or start sending it to the readers. So we decide, we have a principle of keeping our stack nice and simple. That's why we try to avoid using ProxySQL as long as we could. But ProxySQL is a really great piece of software, and it helped us survive the peak during the pandemic, for sure. So we have a system that enable devs to send their writes to the writer node and their reads to the readers, and they can decide where the query should run. They can even send selects to the writers for immediate readback if it's critical to not suffer from any replication lag. So we only put ProxySQLs in front of the writer nodes using CNAMEs. It was relatively easy. The problem was we had only 2 hours until the servers started crashing again. So, and we haven't had a working ProxySQL configuration. So we configured it and put it into production just to see they were all working and the number of connections starting going down. It was probably the riskiest change we ever did on our system, but it helped us keeping our servers up and running. Now, when we started, after we started sending a portion of the write traffic to ProxySQL, we changed the config management, which is Ansible, to support for deploying ProxySQL and Proxy Web. And as a parallel effort, we also made constant changes on the Ansible playbook. For example, we started backing up the buffer pool and restore it during the deployment. This way, we were able to put the machines into production after Ansible considered them ready. So once Ansible changed the tags of our machines ready, then they were absolutely ready to be put into production. They had no replication lag. The buffer pool was warm. We just had to use the same instance type for that to work. We also used an S3 object as a source of backup, so we could start as many readers as we wanted. The maximum number of readers we ever deployed and ever started at once was 70, and all of them were ready over a course of 4 hours. The restore and warm-up time for a 2 terabyte instance is between 3 or 4 hours. That depended on the instance type and the amount of time passed since the backup was taken and streamed to S3. A couple of words about Proxy Web. Proxy Web is a recently open sourced internal tool to visualize ProxySQL. There will be a presentation tomorrow about how you can install it, what are the benefits, and there is also a test environment if you want to evaluate it at home. So actually, Proxy Web helped us and our engineering to hunt for queries and helped us visualize the nature of our traffic. So when we started optimizing queries, it was a really good source of information in addition to Query Analyzer in PMM and Vivid Cortex. Now the problem with Vivid Cortex is, due to legal reasons, we had to stop sending metadata to Vivid Cortex, and while it's still a great tool, it's not that beneficent anymore. Query tuning and optimizing and indexing is an ongoing effort, and but during the pandemic and during this enormous growth, query started running differently. So queries that were okay otherwise started behaving badly. This is because the nature of the traffic has changed. For example, students before the pandemic just log into the site, check their assignments, check their chat, logged out. Now they started spending their whole day on the site, checking the features of Edmodo, hitting endpoints that weren't hit that frequently before. Tables that were relatively small started becoming extraordinarily big, like a table of 2,000 rows became more than 100,000 rows big. And the full table scan on a small table just slipped through earlier when we did our checks, hunting for bad queries. And now we just faced a query that started scanning 100,000 rows every time. So obviously we needed to optimize queries. There was also a problem with uneven distribution of data. Vivid Cortex used to be a really great tool when it comes to hunting these kind of queries down, because you can see all the queries within a certain, running within a certain time, and there are some outstanding ones. Again, the problem is, for legal reasons, we couldn't use Vivid Cortex for that anymore, and we had to parse the slow logs and use QAN and try to figure out how to identify these groups. For example, standard number of a group at Edmodo is between 1 and 2,000 users big. But we started adding all the new users at one point to the Welcome to Edmodo group, and it became 4 million. And suddenly 4 million users were part of that group, causing some of the queries to blow up. We were also getting attacked as we started getting more media attention. And we also had some new, not so well tested queries running due to new feature rollouts. We had an infamous Ops 7082 ticket with 45 optimization related subtasks. And that only covered the most important optimization efforts. The reader's resource usage has been reduced by an overall 10% by fixing indices. This one here, it might be not that visible, started running a day ago back in March. So this was a result of a new feature rollout, and indexing helped a lot, obviously. Now, adding indexes and running DDLs became more and more problematic as the traffic growth. So initially running PTOSC was possible, and we had lower traffic periods. Later, as the traffic growth and more countries went into lockdown, actually the low traffic periods vanished. So there were no low traffic periods anymore, and we couldn't really just ran a PTOSC during the US night, which was usually our peak, the lowest traffic period. As Italy went into lockdown, Europe started producing the same amount of traffic as US, and the same happened in Asia. So we had to be creative, even running simple DDL, and sometimes we just deployed new machines and made the change there, put them into production, remove machines from the production. So we did a rolling change with online alter. At that one point, we either run a failover or run the alter on the master if it was possible. Caching. ProxySQL helps removing connector generated comments like on ping. That's great. It has its own keep alive checks. We cached frequent and mostly aggregation related queries in the memcache or with ProxySQL. We stopped running billions of queries per day this way. And with the help of ProxySQL, we traced one query on the most important writer that was responsible for 16% of the writes. That was an update. There's a form. If you typed something into it, it saved it every 300 milliseconds. Now that number was increased 2 seconds. So you had a chance of losing 2 seconds of content you typed in, but that helped removing a lot of write traffic from our most important writer. Rerouting. As I mentioned, developers had the chance to decide if they want to send the reads to the readers or to the writers for immediate feedback, especially in case of immediate feedback. That was not always optimal because it was just easier. Sometimes it was just easier to send everything to the writers and not dealing with the replication lag. Now, we had many queries on the writers, making it impossible to scale our fleet up and serve more traffic. We started adding readers, but on a couple of clusters, it didn't help at all because the application just simply didn't send anything to these readers. So we used ProxySQL to start offloading these selects. And in case of our backend, we offloaded 70% of the reads to the readers, making it possible to scale up a lot. We did the same. We did the same for all the clusters, and it helped a lot with their performance. Query rewriting. As a parallel effort of our so what we did in ProxySQL was helping a lot, and devs also working on optimizing queries and removing unnecessary code paths, and optimizing cron jobs started causing troubles because of the high concurrency. We also used ProxySQL to rewrite some problematic queries. We removed the majority of the reads from the writers, but still we wanted to make sure that our writers can keep up with the increasing traffic. So we did a traffic, we analyzed the traffic with ProxySQL, and we could identify our mostly written databases and move them to their separate clusters. So with the split, and we used ProxySQL and chain application, and we could execute the split with only making the application read only for 20 seconds. As a parallel effort, we also redesigned the application. We started using bigger instances, so we don't have to use that much disk, because there was one point at half petabyte when we had to ask for a limit increase from AWS. But with the bigger instances, the hot data suddenly fit into the memory, so it started using less I/O. So GP2 disks last longer. And we also wanted to do that so we can make it easier to scale our fleet. As our SQLs and queries were scaling more or less linearly up until a point, we could just throw in one twice as big server instead of two smaller ones. We usually started using R5 ATEX largest for the biggest cluster. And that also helped because we didn't add that many readers to the writer there. And we scaled up to 70 replicas, and then we moved to a 3-tier replication. But actually, we were able to achieve our biggest traffic while having a 2-tier replication. That happened on the 31st March, when we hit the 5 million queries per second. Then we were told to be prepared for 6 times of the traffic, 30 million queries per second. And that was the time we organized our replication to moved our setup to a 3-tier replication that required making changes in Ansible, MHA, and Negios. We there was an ongoing disk increase on data increase on all the servers, and we either deployed the machines with bigger disks or we resize them online, because that's totally possible with EBS, and we have been doing this for years. Actually, you can just do that, wait until the Amazon allocates the extra disk space in the underlying disk subsystem, and then you can just adjust the logical file system. We use XFS. We just ran XFS grow on the partition, and we never ever experienced any performance degradation. This is the final DB flow when we were prepared for 6 times of our peak traffic. So the application sends the writes to the writers. The writer rerouted the reads to a small set of failover pairs / readers. So the failover pairs were the only machines that the writer in ProxySQL sent the selects from the writer. There was a second tier used only as binlog servers, and there was the third tier that was actually serving the reads. With this setup, we could have scale up for reads almost infinitely. When we prepared for this amount of traffic, we had 450 DB servers, 200 R5 ATAX largest in the biggest cluster in a 3-tier application. We used more than 1 petabyte GP2 disk. There were some IO1 disks on the writers just in case. And we always had equivalent reader with the equivalent hardware for the writer in case of failover. We upgraded the hardware under PMM several times, and it served us really well. But when we scaled up to this size, we had to add another instance. So we put the biggest cluster to a separate PMM, and it worked just fine. Later, when we had time to deal with some optimizations, we started zone-aware routing. So we started sending the traffic and keeping the read traffic within the zone, within the same zone, for reducing the cost. We also managed to reduce the ProxySQL CPU usage by 90% with running it with the options idle threads. It helps a lot. If you are using ProxySQL mostly for connection pooling, I strongly recommend you look into this option. We also reduced the threads connected even further, because when we scaled up to the final size of the fleet, actually our backend, there were 6 ProxySQL servers in front of the backend writer, and all of them opened 3,000 connections to the writer. Obviously, there were hundreds of thousands of connections coming from the app. That was still a really reduced number. But because of the MySQL auto increment delay multiplex, it kept them from lowering the number of connections. And that's default by 5. And we don't use MySQL lost insert ID. We also check that with ProxySQL. And when we set it to 1, the number of connections ProxySQL opened to the DB actually dropped back by 10 to 10%. So we actually had 1,500 connections from all the 6 ProxySQLs altogether instead of almost 20,000. That is a really great improvement. Now the current status. We have tens of millions of new users. We built a new site for a country in a new DC to support of the remote learning of 20 million students. And the traffic on the global site is still 5 times of what it used to be. I really hope you enjoyed our presentation, and don't hesitate to reach out to us if you have any questions. And have a great day.